In this video, we'll look at examples of the Laplace transform. In particular, we're going to be looking at signals that have two terms, and as such, they will have overlapping regions of convergence. So this is actually an example from the textbook, example 9.3. So suppose we're given the following signal. X of t is equal to 3e to the minus 2t times the step function u of t minus 2 times e to the minus t times the step function of u of t. And our goal here is to find the Laplace transform, x of s, and its region of convergence. So what we're going to do here is use our previous result, the Laplace transform pair, for the exponential function, which we determined in an earlier video. Now, by inspection, what we can do is we can take this function up here, this signal, and we can take the Laplace transform of each term using this result here. So if we look at the first term here, we see that the exponent, a, has a value of 2. All right, so the Laplace transform for the first term, 1 over s plus a, becomes 1 over s plus 2. And of course, we've got the 3 out in front, which is a coefficient, so we'll put that 3 right here. Likewise, for this first term, the region of convergence, sigma, has to be greater than negative a, and since a is 2, we have the region of convergence for this first term is sigma greater than negative 2. All right, now let's move on to the second term. The second term, we can look again by inspection and see that a in this case is equal to 1. So we have 1 over s plus 1, and we have a 2 out in front for a coefficient, so we have the 2 here. And of course, remember there's a minus sign between the two terms, so there's the minus sign here. For the second term, the region of convergence is sigma is greater than negative a again, and in this case a is 1, so we have sigma greater than minus 1. Okay, so now we have our two terms, and we also have their corresponding regions of convergence. Now, each term has its own region of convergence. However, the region of convergence for the entire Laplace transform, x of s, has to satisfy both of these terms, the first term and the second term. So that's only going to happen if the region of convergence is the intersection of the individual regions of convergence. Okay, not the union, but the intersection. So in other words, total region of convergence is equal to region of convergence for term 1, intersection with region of convergence with term 2, and that gives us sigma has to be greater than negative 1. So our result then, here's our Laplace transform. X of s is 3 over s plus 2 minus 2 over s plus 1. And if we want, we can combine this using least common denominators into a single fraction like this, s minus 1 over s plus 2 times s plus 1. And our region of convergence for this transform, sigma, has to be greater than negative 1. So let's go ahead and plot this in the S-plane to show a pole 0 region of convergence plot. First of all, notice here in our final form of the transform, we can see that we have a 0 by setting the numerator to 0 at s equal 1. So we're going to plot that right here. There's our 0. And we have two poles. We can get that easily from the denominator here. The first pole is when this term goes to 0. That's when s is equal to negative 2. So there's that pole right here. And the second pole at s equal negative 1. There's the second pole there. And then finally, our region of convergence, remember, is sigma greater than negative 1. So it's everything to the right of this pole here. So that's this whole region shaded here. I'll just make a note here that this is a right-sided signal. In other words, both terms are going to the right. And the result is the region of convergence is a right half plane. Okay, now let's look at a different example. In this case, we have x of t is e to the minus 3t times u of t plus e to the 2t times u of minus t. And again, we're going to find the Laplace transform x of s and its region of convergence. Now, notice this one's different. This first term here is a right-sided signal. We can see that by u of t, which goes to the right. The second term, however, is a left-sided signal because it's u of minus t. This is a time reversal, meaning the step function points to the left to negative values of t. So what we're going to do here is use our two results from earlier in these lecture notes where we found the Laplace transform for a right-sided signal, like what we just did on the previous slide. And also we're going to need for the second term the Laplace transform for a left-sided exponential signal. That's this one here, which has a Laplace transform that has a negative sign in front of it, and the big difference is the region of convergence is sigma less than negative a instead of sigma greater than negative a. All right, so all we have to do then is use these two results here, and by inspection, we can see for the first term, we have a equals 3 up there. So we have 1 over s plus 3, and the region of convergence is sigma greater than negative a. I'm getting that from right here. So we have sigma greater than negative 3. For the second term, we have this term here. Now remember, this is a left-sided signal, so we have to use this Laplace transform right here. And notice there's a minus sign out in front of it, so we pick up the minus sign right here. Also, notice by inspection, a is equal to negative 2, all right, because we have a positive 2 up in the exponent there. And with a equal negative 2, we have 1 over s minus 2. And remember the region of convergence for a left-sided signal, sigma is less than negative a. So in this case, the region of convergence is sigma is less than 2. Now, we have to take the intersection of these two regions of convergence. All right, so what we end up having here is sigma is going to be between negative 3 and positive 2. Likewise, for x of s, we can combine these two terms using least common denominator, and we end up with minus 5 over s plus 3 times s minus 2. We have two poles. We have a pole at negative 3 right here, and the second pole for this term is at s equals positive 2. That's shown right here, and there are no zeros in this particular case. So the region of convergence, remember, is between the two poles. So we end up with a vertical strip between the pole at minus 3 and the pole at positive 2. And this will always be the case for so-called two-sided signals. Remember, our original signal up here had a right side, the first term, a right-sided signal, which is this one here, and the second term corresponds to a left-sided signal here. So taken together, they form a two-sided signal. Finally, the last thing we'll do here is we'll actually see an example where the Laplace transform doesn't exist. There are cases where there is no Laplace transform. So in this particular case here, we're given this signal. Again, it has two terms. It has a right-sided signal, e to the 3t times u of t, plus, and that's shown here, by the way, over here on the right. And then we have the second term is e to the 2t times e to the minus t. And that's this left-sided portion going here. Now, when we use the results from the previous slide to do the Laplace transforms of these two signals, we get 1 over s minus 3 for the first term. That's where a is equal to negative 3. And for the second term, this is the left-sided signal. We have minus 1 over s minus 2, where a is negative 2. Now, the region of convergence, this is where we run into a little bit of a roadblock here. The region of convergence for the first term is sigma is greater than 3, but the region of convergence for the second term is sigma has to be less than 2. Now, there's no intersection between these two regions of convergence. We can't have a number that's greater than 3 and less than 2. So there is no region of convergence. Therefore, the Laplace transform for this particular signal does not exist.